Hello everyone, I'm Harsh Kashyap, and along with my team members Abhishek, Prashant, and Ayush, we are excited to present our project on forecasting for groundwater in India under the guidance of Dr. Raman and Dr. Shobha. Now, the supply chain is the backbone of seamless resource distribution. Groundwater, a critical resource in India, requires effective management and forecasting. Our project integrates supply chain analytics with groundwater forecasting to enhance water distribution efficiency, reduce wastage, and support informed decision making. Now, the motivation behind this was India faces severe water crisis during summers despite being home to major rivers and high rainfall zones. Unplanned usage and wastage of water leads to this situation. Though power forecasting and supply chain optimization, our project aims to support sustainable groundwater management, ensuring water availability across the regions. Now, the tools and technologies which we have used in this pre-processing, we have used Python, which includes Pandas, NumPy, Matplotlib. Apart from that, for forecasting model, we have used LSTM, that is long short-term memory. And for supply chain optimization, we have used linear programming and heuristics. For visualizations, Matplotlib and Seaborn. And for risk classification, we have used machine learning techniques. Now, coming to this literature survey, that is supply chain optimization studies, a literature review and classification. So basically, in this review of the research was we analyzed the trends, methodologies, and the problem-solving approaches in supply chain optimizations. Apart from that, various decision levels were there, which were categorized research into strategical, tactical, and operational, aiding to the long-term planning, resource allocation, and real-time decision making, and other optimization techniques, which includes heuristic and linear programming and genetic algorithms. Now, the challenges and future scopes we got from this literature survey were like highlights the research gaps in global supply chains, disruptions, and demand uncertainties, suggesting future AI-driven solutions. Now, the key takeaways which we got here is a foundational study on supply chain optimization, which helps businesses efficiency, enhance efficiency and decision making. Now, I will present the other surveys.
So my title is on big data optimization and management in supply chain. So the findings are in impact of the big data enhances demand forecasting, inventory optimization, and risk management. The key technologies used is AI and machine learning that improves the warehouse management, market prediction, and efficiency. The IoT applications used are real-time tracking and reducing losses. The benefits we can think of faster deliveries and cost reduction, better risk prediction and operational efficiency, and improved customer satisfaction. The big data analytics is transforming the supply chain into the more agile, efficient, and resilient systems. Next clip is. The third literature survey is on sustainability and optimization of the supply chain. So it usually focuses on the reducing the environmental impact and promoting the ethical sourcing. It has the green logistics and renewable energy as the key strategies. Also, it has a circular economy and reverse logistics that encourages the recycling and waste minimization by using reusing the materials and components. The multi-objective optimization models helps to balances the cost, quality, and sustainability to optimize the decision making. So sustainability is the critical for the future of the supply chain. And integration of the eco-friendly practices and ethical sourcing enhances the efficiency and reduce the environmental damage. Now, next is done by my friend Abhishek.
So today I will be discussing the key gaps in traditional demand prediction and how we are addressing them to drive growth. Previously, predictions relied only on past groundwater levels. However, we now incorporate additional factors like rainfall, population growth, land use, and industrial water consumptions. Earlier, the focus was solely on predicting demand. Now we go beyond that by optimizing supply. We achieve this by considering pipeline leakage, infrastructure quality, and energy cost, ensuring a more efficient and cost-effective distribution. Traditional models were static and couldn't adapt to real-time changes. Now, with the use of LSTM networks, we can generate dynamic and time-sensitive predictions, making our forecasting much more responsive to evolving conditions. Predicting alone are not enough if they don't lead to action. That's why we now classify high-risk areas, enabling policymakers to take preventive measures and make informed decisions to ensure sustainable resource management. Uh, Now I will tell the methodology. So the first step is the cleaning and normalize raw data for better model input. The second step is to extract key factors like weather, population, and industry trends. The third step is LSTM-based demand forecasting, which use deep learning for accurate real-time demand predictions. The fourth step is supply chain optimizations, which improve efficiency by reducing losses and optimizing resources. The fifth step is classification and insights that identify high-risk areas to support informed decision making. Now the further things will be explained by my friend Prashant.
So I'll be explaining the output part, like what the output that we have obtained and what are the various graphs that we have obtained from the data. As you can see in the first thing, we have obtained the relationship between the actual extraction as the predicted extraction. The actual extraction is the red line, and the prediction extraction is the dotted lines. Those are the extractions that we have made. And at the right side, you can see the ground scarcity risk levels on like at various districts. Around 100 districts are at moderate rate, and zero districts are at safe rate, and around 600 districts are at critical rate of having groundwater scarcity. Next. Here we can see the state-wise critical groundwater scarcity, in how many states, and in that particular state how many districts are facing actually the groundwater scarcity problem. We can see here over here, like in Uttar Pradesh there are around more than 60 districts which are having this problem. In Madhya Pradesh there are more than 40 districts that are facing this problem, as well as in Rajasthan, there are around like more than 30 districts that are facing the same groundwater scarcity problem. In Tamil Nadu, there is an average around 30, and as we go down around, you can see at Arunachal Pradesh, there is around more than 10%, around 15 number of districts that are facing groundwater issue. And as we go down, they can see that, and Diu and Daman, there are zero districts that are facing the issues. So this is basically the state-wise number of districts that those are facing the groundwater scarcity issues. Next, this is the feature map that or the heat map that we have created from the Python code. It basically giving us at various levels where, as we can see, recharge from the rainwater during monsoon, and for that we have got the relationship for various things. Next. This is the mostly the important part of a real. These are basically the most important output that we have obtained. We have used Facebook profit model, forecasting model for forecasting. You can see for Andhra Pradesh state, where we have like when we see we have done the forecasting from starting from year 2000 to year 2024. The red dotted lines actually indicate the forecast, like the predicted forecast, and the actual demand is the blue line. We can see same for the Assam thing, the actual thing and the predicted thing, and same we have done for the Bihar, like what's the liter of groundwater requirement that would be requiring as we go through the years. And we have at the last, you can see for Arunachal Pradesh, due to some data inconsistency, we were not able to get the exact graph. So there is some inconsistency in the graph. Next. So basically, this is indicating over years for the overall groundwater scarcity, groundwater demand in India, as we start from zero and it goes till 140. And the left hand side on the y-axis, it's the number of liters that would be requiring in future. The dotted line actually, blue dotted line actually indicates the actual demand. What is the actual demand? That is the existing demand, and the red thing is the predicted demand in the future, as how we goes through the years. And we have done this through using LSTM forecasting thing, machine learning. Next. Summary, we have done the data pre-processing where we have cleaned the data, handled the emitting data, and normalized the features. We have added we have like feature we have done feature engineering. We have like basically we have added rainfall, the land use, initial water use to improve accuracy. We have done the demand forecasting using the LSTM model and evaluated the progress. Supply chain optimization can be also done. Like some of the suggestions are like pipeline leakage detection, improved infrastructure, and optimized distribution on like throughout the districts and throughout the states, which actually avoid groundwater scarcity. We have also identified the main high risk areas, like how the main the high risk districts where where the districts are basically facing majority of groundwater scarcity issues, and we have already insights for that thing. Next. And in the conclusion, we have successfully implemented a groundwater demand forecasting using the LSTM model. And basically, we were trying to like just to optimize or the groundwater supply chain by integrating. We have also like, integrating external factors such as rainwater in this particular district during monsoon, during winter, and what's the actual requirement, and what's the actual requirement according to district wise as well as according to state wise. And we have tried to improve the prediction accuracy, and we have done the risk identification in many districts or many states where they can actually face groundwater scarcity. Key impact are more accurate demand forecasting, improved water distribution, and actionable insights for high risk areas. Next. Now we will be going to the coding part, like mainly what have we implemented in the coding part. So basically, we have used Python for the mainly for our coding stuff, and we have just extracted the data from the Excel thing. In the Excel thing, we had data related to the name of the state, the name of the district, recharge of rainwater during the monsoon season, recharge of other sources during the monsoon season, recharge of rainwater from both monsoon and monsoon season, total annual groundwater recharge, total natural discharges, on annual groundwater extraction, current annual groundwater extraction for irrigation, current annual groundwater extraction for domestic and industrial use, and stage of groundwater extraction and the percentage. Like the stage is basically the percentage of groundwater extraction in for those particular district and those particular state. So this is what we have done. We have in our data set, and we collected the data set from the data.gov website, and it's we got it from the government website itself. And we have like the main features that we have focused on is the recharge from the ground, recharge from rainwater during the monsoon season, recharge from rain during the non-monsoon season, and recharge from other sources, and the total annual groundwater recharge, total annual discharge, total acceptable annual groundwater discharge, current annual groundwater extraction for irrigation, current annual water extraction for domestic and industrial use, current annual groundwater allocation for domestic use as on 2025, net annual groundwater availability for further use, and the stage of groundwater extraction, that is the percentage of groundwater extraction for that particular district as well as for that particular state. We have implemented the cyclic learn model thing, and we have basically tried to find out the accuracy thing through this. Basically, we have tried to find out the S1 score, the precision score through this. Next. Next. We through this to using the matplotlib library, we have using the scatter plot as well as the line plot. We have tried to create a relation between the actual extraction as well as the predicted extraction, like what are the actual extraction in liters as well as the predator extraction that would be required in bin liters. Next, and later on, we have using Matplotlib itself, we have tried to find out the high risk areas based on the giving a certain where we are given certain condition. If there is a extraction of water more than a certain level, so it would be counted as a high risk area. It would be counted as a critical area. It would be counted as a moderate area. By calculating this, we have come to a conclusion like the total counts of districts in India around 100, around less than around 95 to 100 districts in India are at a moderate stage of having groundwater scarcity, whereas zero are at a safe. No district in India is at a safe level. And when we talk about the critical thing, there are around 600 districts. Those are at a critical stage of having groundwater scarcity in India. Later on, using again the Matplotlib Seaborn thing, we have tried to create a relationship between the state and the number of districts those they are that they are having who are facing the groundwater scarcity issues, starting from Uttar Pradesh, Madhya Pradesh, Rajasthan, Gujarat, Tamil Nadu, Telangana, Karnataka, Chhattisgarh, Odisha, Bihar, Maharashtra, Jharkhand, J&K, Punjab, Haryana, Karnataka, Arunachal Pradesh, Delhi, Nagaland, Assam, Meghalaya, Manipur, Lakshadweep, Mizoram, Himachal Pradesh, Tripura, West Bengal, Uttarakhand, and Sikkim and Diu Dam and Goa. We have tried to collect data from all these states and tried to create the number of districts in those states that are facing groundwater scarcity issues. These are basically the stuff that we have done to we have done the model training. This is the above thing, LSTM. Scroll up the LSTM thing. Go to the LSTM thing. First thing. Yeah, fine. So basically, where we actually, as we told earlier, we implemented the LSTM model. Like we are through the data points, like starting from 0 to 140 data points. We have done the prediction, like the groundwater demand forecasting as we go through the years, where the blue line is the actual demand, that is the present demand, and the red line is the predicted demand for the future thing. Next. And for the state-wise forecasting, we have implemented Facebook Profit because we were actually getting good prediction from using Facebook Profit. So we can, as you can see, for Andhra Pradesh, we have done the forecasting thing starting from. We have mainly selected the main few states, main four states, and we have done only for those states the forecasting thing for the groundwater thing. Like you can see, start from year 2000 and it goes till year 2024, and predicting the ground level demand that would be that would be requiring throughout the years, where like the red dotted line indicates the forecasted thing that we have doing, and the blue thing is the actual demand. Next, same thing we have done for like Assam, where we have done where and same thing we have done for Bihar. So mainly we had implemented the LSTM model and the Facebook profit thing, and we done the estimation, state-wise estimation as the total estimation for predictions.